Now for hydrogen, we already found that Gi plus 1 over Gi is equal to half. So this prefactor cuts. Simply have N for hydrogen then, 2 Gi plus 1 over Gi is equal to 1. Now the only states are Ni equal to N of hydrogen 1, this is the neutral state, and Ni plus 1 is N of hydrogen 2, which is the ionized state. And the number of electrons then is equal to the number of ions. Therefore, the Saha equation becomes N squared, the number of ions over the number of neutrals, is then equal to 2 pi mkt over h to the cube, and the exponential of minus chi to the minus chi over kt. So this solves the problem of ionization of hydrogen. To make sense of the number, let's write the ionization fraction. Let's define the ionization fraction, call it x, as the number of hydrogen ions over the total number of atoms, which is H1 plus and H2. So we have an equation for the square of the number of ions over the number of neutrals. You can write that in terms of the ionization fraction. It comes in square of the ions over the n of the neutrals. If you define NH as equal to the number of the total number of hydrogens is the number of neutrals and ions, then you can write the number of neutrals as the total number of hydrogen minus the number of ions. Now extract the number of hydrogen atoms so that everything is divided by it. And that is the ionization fraction in there. So what you have here in the end is the total number of hydrogen atoms over x squared minus 1 minus x over 1 minus x. So Saha's equation is giving you that quantity here, n squared, n of hydrogen, x squared over 1 minus x. Now the number density in terms of the mass density is rho over the mass of the hydrogen atom. So we can write this equation as square the number of ions over the square over the number of ions over the number of neutrals is equal to rho over the mass of hydrogen times x squared over 1 minus x. So this equation is a quadratic. If you multiply and divide both sides by mh over rho, then what you have is, now if you call what is in the left-hand side alpha, this equation simply then becomes x squared plus alpha x minus alpha is equal to 0, or alpha then is equal to. So we can solve this quadratic. The quadratic is simply square root of alpha squared plus 4 alpha minus alpha over 2, the quadratic formula, where we discarded the physical negative root. Now the solution to this equation for a set of densities is shown here using the ionization potential of hydrogen, which is 13.6 electron volts. You see here, it depends on the density. These are the curves for the blue is 10 to the minus 9, 10 to the minus 10, 10 to the minus 11, and 10 to the minus 12 grams per cubic centimeter. You start to see here that for densities of about the sun, which is 10 to the minus 9, you have at 10,000 Kelvin, about half of the atoms being ionized, as we saw before. So if you combine this with the curve of excitation, so the excitation was this one. You have here the number of atoms in the ground state and the number of atoms in the first excited state. They cross at about 10 to the 5. But at 10 to the 4 Kelvin, you start to ionize really heavily. Now, if you combine them both, excitation and ionization, this is the curve that you have, peaking at 10,000 Kelvin. This is again the curve for different densities. For solar densities about 10 to the minus 9, you start to have ionization and the excitation and ionization balance peaking at about 10,000 Kelvin, as you see here. So that gives you the maximum strength of the Balmer lines.